deterministic data flow is deterministic. Programs that give the same inputs will give the same outputs. But let's take a closer look at what this really means. And there's another concept lurking there called non-determinism that's very important that we have to understand. So first of all, in a deterministic data flow program, every thread always executes the same instructions in the same order. So this is true even though the threads might have different speeds in different executions. In fact, speeds can vary in a real computer because of different reasons. There are different sources of timing changes. For example, I/O, which can arrive at any moment, which changes how the timing works. Hardware interrupts by hardware clocks, which can arrive at any moment. Things like cache misses, which can cause certain things to take longer than they might otherwise take. And other sources of timing changes. For example, if your computer is running many programs in different processes at the same time, this can cause interference that changes the timing, and so on. So the speeds can vary. But a deterministic data flow program always gives the same outputs for the same inputs, despite any of these variations in the thread speeds. We say that the program has no observable non-determinism, or another way to say it is that it has no race conditions. This is in fact a major advantage of the deterministic data flow paradigm, and it's not shared by the two other paradigms, message passing concurrency and shared state concurrency. Let's now talk a little bit about non-determinism, this thing that the deterministic data flow paradigm somehow avoids. So non-determinism is the ability of the system to make decisions that are visible by a running program. The point is that it's the system making the decisions and not the application programmer. Usually, an application programmer writing a program is a complete master over what the program is doing. Well, non-determinism is a case when this is not true. In certain cases, it is the system that makes the decision. All the programmer knows is which are the possible decisions, but the actual value of the decision is not known until execution. So the decisions can vary from one execution to the next. In terms of concurrent programming, the part of the system that actually makes these decisions is called the scheduler. This is the part of the system that decides at every instant which thread to execute. Well, this decision is not made by the programmer, it's made by the scheduler, which is part of the system. So this decision is called non-determinism. Okay? Non-determinism is a property of any concurrent system. Since concurrent activities are independent, well, we can't know which one is happening before the other because they're independent. If we knew that one would always be before the other, they would not be independent. That would be a dependency. And because they're independent, we really don't know the relative order, and that means any relative order that occurs during execution is decided by something outside of the program. So it's non-deterministic. Okay? Non-determinism is a property that is very important because it can give huge problems if it's not carefully managed. So a crucial part of any concurrent programming is you have to manage the non-determinism. So here's an example of a non-deterministic program. Declare x, and then I have two threads, one doing x equal 1 and the other one doing x equal 2. Now, I do not know the relative execution order of these two threads. I know that the first thread will be created before the second one because the two thread creations are done in the third thread, but I don't know what's going to happen with the two bindings x equal 1 and x equal 2. They can execute in any order, which means that x will be bound to 1 or to 2. We don't know which. And when the other binding is done, there will be an error because variables can only be bound to one value. No? So this is an example of non-determinism. The choice is made by the system. In this case, the choice is visible because we see it in the different value of the binding. So here's another example with a cell. So we have a program which is very similar. We declare X as a new cell, and then in 2 threads, we assign the cell 1 and we assign 2. Again, the execution order of the 2 threads is not fixed. The 2 assignments will be done in any order. The cell X will first be bound to one of the 2 values and then to the other. And after both threads terminate, the resulting value of X will be either 1 or 2, but we don't know which. In this case, there's no error. This is again an example of non-determinism, a choice made by the system during execution, and in this example program, we can see the effect of the choice. It's not always possible to see the effect of the choice. So here's a small variation with a cell. Well, both of them are doing a binding, an assignment to 1. So the system is still making a choice, but in this case, both of the results are the same. But it's still non-determinism because the running program is making a choice. There is a difference in the execution order of the 2 threads decided by the scheduler. This choice still exists. In this case, the results are the same by accident, but the choice remains. Okay? Now, non-determinism has to be managed. Non-determinism is an enormous source of errors, especially if it's unwanted, unmanaged, can appear at any time. In fact, the most complicated case, the hardest case to manage non-determinism is when both threads and cells are used in the same program, like in the previous example. The reason is that the cell content changes with time, and if 2 threads do an assignment to the same cell, depending on the relative execution, the final content of the cell will be different. Okay? And because you can do many assignments to cells in 2 threads, you can have a huge number of possible different interleavings, different orders. So this is extremely hard to manage. So by far, in fact, the most complicated case is threads and cells together. I compare it to hydrogen and oxygen together. It's an extremely explosive mixture, whereas each one of them separately is not. And the same with threads and cells. Only threads is not a problem. Only cells is not a problem. When you have both of them together, you get huge amount of exposed non-determinism. Okay? This is where deterministic data flow has a major advantage, since it does not have cells. It only has threads. The result of a program is always the same. No observable non-determinism. Despite all these possible interleavings, you don't see any difference. Okay? Except, there is one exception, if there's a programming error. If there's a programming error, an exception will be raised, and then you will see. So the error introduces non-determinism, in fact. It introduces observable non-determinism. So there are ways to manage that, but basically, assuming your program is correct, like the pipeline programs I showed before, there will never be any observable non-determinism. In fact, whatever the scheduler does, all the non-determinism of the scheduler does not affect the result. And this is really a major advantage of deterministic data flow.